So yeah, I mentioned that for pseudo-perfect modules, we at least have the isomorphism of Hochschild homology, but for general localizing invariants, the behavior is very poor. So what I will explain below is the recent definition of the category of nuclear modules in the special case of affine Assyrian formal schemes. This is due to Clausen and Scholze, and this category is dualizable, presentable. In fact, I think this result is unpublished at the moment, and its compact objects are given by just the usual perfect complexes over the completion. And the point is that this category behaves much better. In particular, the restriction to an open subset, for example, principal open subset, let's say, becomes a localization in this framework, which is not true at all for the usual perfect complexes. Okay, and the main goal of the talk will be to produce a much more general construction for proper DG algebras. Okay, so now I will recall some general notions like presentable categories and dualizable categories. So we will mostly ignore set theoretic issues just for simplicity, but in practice they can be solved by considering sufficiently large regular cardinals and proving that you have some sort of stabilization, that the construction doesn't depend on the choice of the cardinal. So recall that the category is presentable if it is pretriangulated, if the homotopy category has small direct sums, and there exists a regional cardinal kappa such that the triangulated category is generated by kappa compact objects. Well, yeah, I should say by a set of kappa compact objects. So the object is kappa compact if for any small family of object y sub j, and for any morphism to a direct sum of y sub j, there is a set of subset of j with cardinality less than kappa, such that f factors through this direct sum of yi over I. In particular, if this kappa is just omega, then you get the usual compactness.
So sir, could you remind what is a regular cardinal? My set series.
Well, it's basically a technical, but important assumption that it's not a sum of smaller.
It's not important. It's not really important.
Yeah,
we have to believe that smart people know how to say the correct words.
Yeah. Yeah, Maxim, so it's just some technical notion which should be just a basic requirement here when considering such.
But it's always be uncountable,
yeah. Okay, so the functor is called continuous if it commutes with small direct sums. And we will denote by DGCAT continuous the infinity category of presentable DG categories and continuous functors. There is a natural symmetric monoidal structure on this category, the so-called Lurie tensor product, which is defined even in the more general setup for non-additive categories, non-stable infinity categories. But here it's uniquely determined by the internal home given by basically the categories of continuous functors. So continuous functors is the full subcategory of the usual functors from C to D. And we will denote this tensor product by tensor hat. This is probably not standard notation, but just to avoid confusion with the usual tensor product. So we have a full embedding of continuous functors from this Lurie tensor product. They embed fully faithfully into the usual functors from the tensor product of C1 and C2 to D. So the insertional image consists of bicontinuous bifunctors. Definition of dualizability is basically the requirement that this category is a dualizable object in the symmetric monoidal category continuous presentable digicategories with Lurie tensor product. I will actually, there are a lot of ways to formulate dualizability, and I will not even need this particular way. So if you know what is a dualizable object, then you know what is a dualizable category. But anyway, I will formulate a lot of equivalent, several equivalent characterization of this property. And important remark that dualizability property doesn't depend on the base ring. So you can consider categories over integers or over even infinity categories over, just categories over the sphere spectrum. This property, if it's satisfied over some base ring, then it is satisfied over the sphere spectrum. So K is more or less irrelevant here. Okay, so now there are several equivalent formulations. Actually, I mentioned only part of them. There are more equivalent ways to formulate dualizability. So the following conditions are equivalent. So C is dualizable, then there is a short exact sequence of the form C goes to modules over some DG algebra A, then extension of scalars to DG modules over B, where the morphism from A to B is a homological epimorphism. So in other words, we can represent C as a kernel of localization of compactly generated categories with continuous right adjoint. And equivalence, you get the same condition when you deal with small DG categories instead of DG algebras. So just the same. So this equivalent to having just one object. So another formulation is requiring that C is a retract of compactly generated categories inside this category of continuous functors between presentable categories. And another formulation is that the Ionida embedding from C to models over C has a twice left adjoint. So the first left adjoint is given by the K-limit functor if you think of modules as int objects. And the point is that there is a twice left adjoint, so one more left adjoint. And another way to formulate the same property is by requiring that if you have any continuous localization of presentable DG categories from D to C, then you have a continuous section, which is not necessarily fully faithful. I mean, you of course have a section given by the right adjoint, but right adjoint doesn't have to be continuous. I mean, it is fully faithful, but not necessarily continuous. But here you require that there is continuous section, but you don't require fully faithfulness. So these conditions are all equivalent. If there are any questions at this point, I'll be glad to answer.
So dualizable means that inner home to any other category is a tensor product, yeah?
Yes, a tensor product of the dual.
Okay, yeah. Oh, yeah, kind of.
Yeah. Okay. And also in this condition 6, you can consider instead localization, just arbitrary localization from D to D prime, and you can formulate that any continuous functor from C to D prime can be lifted to a continuous functor from C to D. Okay. These are equivalent formulations. Well, probably the most important is the second formulation, at least for us. Well, more precisely the third, technically speaking. Okay. So we call a continuous functor strongly continuous if its right adjoint is continuous. And we denote by digicategories dualizable the non-full subcategory formed by dualizable categories and strongly continuous functors. And so now an important observation is that we have a fully faithful embedding from small triangulated digicategories inside dualizable presentable categories. So with this strongly continuous functors. So A goes to models over A. So it's important that it's fully faithful. No, there are no new functors in this dualizable framework. So for the tensor product, we have that if we multiply the categories of models over A and models over B, we get models over A tensor B. And for a homological epimorphism, the dual category can be described as the kernel of the extension of scalars between left models. You can also describe what is the tensor product of such kernels in terms of certain fiber products, but I will not need this. So another important observation here is that condition 5 of this theorem gives a canonical short exact sequence. Again, strictly speaking, you need to choose cardinals, but if we ignore this, then there is a short exact sequence. So C goes by twice left adjoint of the unit embedding to models over C. Then it goes to models over some digicategory. I mean, it's more or less immediate that the quotient by the image of this twice left adjoint is completely generated. So this is models over something. And this continuous Kalkin category can be described as the Karuba closure of the image of the cone of the natural map from twice left adjoint of the Yaneda to Yaneda. Okay, and this canonical short exact sequence allows, in particular, to extend localizing invariants, in particular, define continuous K-theory for dualizable categories, and more generally for any define a continuous version of any localizing invariant. And so we basically apply, for example, non-connective, here I mean non-connective K-theory, apply it to the Kalkin category, and then take the loops, which means just shifting by -1. And then you can formally check that it is again localizing invariant. And it's essentially a unique extension of K-theory to dualizable categories, so that for compactly generated categories, we get K-theory of the compact object. And for a homological epimorphism, we can make a much simpler definition just by defining this continuous K-theory to be the fiber of the map from K-theory of A to K-theory of B. But then, if you do it this way, then you need to check the independence and also functoriality of this construction under strongly continuous functors. But if you do it this way, then everything essentially comes for free. Are there any questions at this point?
Will you explain at some point how you apply this technique in the real world? So of course it's all very nice abstractly, but probably you need some concrete life situations.
Well, with this continuous K-theory, I will not mention this probably in this talk. I mean, I don't have it in the slides, but I have, for example, computation of this continuous K-theory for sheaves on locally compact Hausdorff spaces, for sheaves of models.
And what is the answer?
The answer is, for example, you take a sheaf of pre-sheaf of DG algebras on locally compact space. Then to get the K-theory of the category of sheaves, you take the pre-sheaf of just K-theory spectra of this DG algebras, you sheafify it, and you take sections with compact support.
Okay, it's still not an. This is not an explanation that is easy to grasp. Now, are there some real-life examples in a more algebra geometric world. For instance, at some point you mentioned the formal completion of P1 inside P2. Does this abstract nonsense help you to deal with this formal scheme? Or with something else of similar level of concreteness?
Yeah, for formal schemes, there will be a, well, it's unfortunately a conjectural expectation. I don't know, maybe there is some progress. This unpublished work of Clausen and Scholze, but there is some expectation that K-theory of nuclear models should be basically inverse limit of K-series of infinitesimal neighborhoods. But it's at least I don't know how to prove it. Maybe they already succeeded in it.
No, but this is already very good information. This means that
yes.
Very good mathematicians expect this to be true. And so you say, suppose I don't really have a good feeling of K-theory in general, but I have some feeling. And then we can pass the projective limit. And indeed, if you have a formal scheme, then you can represent it as an inductive limit of usual schemes, take K-theory of each scheme, and then they form a projective system, and then you form the projective limit of K-theories. And then not quite a theorem, but there is a reasonable expectation that this projective limit is in fact this type of K-theory, continuous K-theory of something else.
Yes.
This is good.
Yeah.
Also, Sasha, just a little example. If mod A describe you like some scheme of finite type, and mod B is open subscheme, mod B, then this kernel will be what? It will be formal.
No, but it's just shift. I mean, quasi-coherent shifts supported on.
Quasi-coherent shift supported on the
closed subset. Yeah.
Yeah, I see.
Yeah, but this is a situation when you have just localization. I mean, just the usual quotients of on the level of compact objects. You don't have to consider large categories. Okay. So this is a brief remark about defining localizing invariance for dualizable categories. Now. I will give just two classes of examples. One is given by certain just associative version where you drop commutativity of the basic setup for almost mathematics. So you can take an associative ring and decide it ideal such that it squares to itself, and additionally assume that I is flat as a left or right R module. Then the direct tensor product of I with itself equals I, and it follows immediately that the map from R to R mod I is a homological epimorphism. So you have a dualizable category, which is the kernel, which is actually derived category of almost modules in this, in the commutative case. And moreover, if you assume that I is contained in the Jacobson radical, so if 1 plus I is contained in invertible elements, then this category has no non-zero compact objects. It's basically Nakayama lemma. And another class of examples, which I already mentioned, is given by sheaves on locally compact Hausdorff spaces. So if X is locally compact, you can take a presheaf of DG rings on X or presheaf of small DG categories. And then the DG category of sheaves of modules is dualizable. And its dual is given by the sheaves of left modules.
For instance, you can take this presheaf of DG rings to be just the constant sheaf Z.
Yes, yes.
And then it's a kind of exercise if you want to really understand the notion of dualizable categories. And well, and of course, my personal request would be to start with baby examples when something equals Z, and then to say that you can replace Z by a presheaf of DG rings, not the other way around, because otherwise it's hard to understand.
Yes, that's right. In fact, the case when this is the constant presheaf with fiber Z is actually the crucial. If you understand this special case, then you can also prove this general version. There are several ways to prove the dualizability, but I mean, the most direct way, if you construct a coevaluation and evaluation directly, it proves dualizability, but it does not explain how to compute, for example, continuous K-theory. And to compute continuous K-theory, you need some more careful analysis of what happens. So, I mean, there are several ways to prove that this category is dualizable. But yeah, I will not go into details in this talk. So, I'm just mentioning this as an example here. And I guess this is due to Luria, but I think I first learned it from the notes on Vladimir's homepage in the case of DG categories. Okay. So now I want to give a non-example just to explain that we need to be careful when considering these kernels. So if you don't require this morphism of DG algebras from A to B to be a localization, then this kernel doesn't have to be dualizable. So I mean, in fact, you get some quite random presentable category, and just a nice exercise. You can take a fine plane and restrict to GM contained in one of the coordinate axes. So you take this morphism from polynomials to Laurent polynomials. X goes to T, Y goes to 0. And then, in this case, the kernel is not dualizable, but it is still it fits into a short exact sequence. It's somehow an extension of two completely generated categories, but still it's not dualizable. And this is, I guess, a nice exercise to also understand what's going on with this dualizability. And in general, let us make one more trivial observation that I mean, of course, we know that if this is a homological homomorphism, then the kernel is dualizable. But also, you can just assume that it's a homological homomorphism onto its image. Then the kernel is still dualizable. I mean, this is obvious, but this we will encounter this later. Okay, are there any questions on this?
Just a second, I want to listen to your example. You have kind of complicated example of fine plane and punctured line inside, yeah?
Yeah.
But if you just consider B as a closed line, it will be dualized.
No, then it's just shift on A2 A1.
I see, yeah. Okay.
Yeah, but yeah, you get something non-trivial when you do this restriction to the locally closed subset. So I mean, for this kernel of restrictions to locally closed subset, they don't have any reason to be dualizable, and in general, they're not. Okay, so now I will define the category of solid modules in the case of affine formal scheme. formal schemes. So again, we take an Assyrian commutative ring and take some ideal. So this nuclear models will form a full subcategory in the derived category of solid models. And in this definition, I will not recall the theory of condensed sets and condensed abelian groups. I will just directly define this. I mean, it would require much more time. So I will directly define the derived category of solid models. And in fact, this definition is quite simple. And so this will be a compactly generated, locally presentable category, technically speaking. And we will describe its subcategory of compact objects, which was describes the category. So the collection of compact generators is given by the object of the form product of copies of the completion, where S is some set. So for now, this is just the symbol, but now, but the product will be indeed the product. And the morphisms are defined as follows. So when we have two such products, the morphisms are given by the product over T of limit over N of direct sums over S of copies of R mod I to the N. So in other words, you can just assume that the target is just one copy of this completion. And then you basically, you can put topology here, the usual topology, and then it's basically in the special case, let's say of for example, p-adic integers, you take morphisms of pro-p groups. This is quite intuitive definition of morphisms, and so by definition, these objects, they form an additive category, and derived category of solid models can be defined as a derived category of right models over this category.
Sasha, unfortunately, I didn't attend the talks by Scholze and Clausen.
Yes.
So I want to understand this example at a slower pace. So suppose that R is Z and I is generated by P, then the completion is ZP.
Yes.
And now you suppose your S is the set of integers. And T is a singleton, just a set of one element. Then you are defining the set of morphisms from, so you have a certain ZP model, namely the set of all sequences with formed by the set of all sequences of p-adic integers.
Yes.
And then you want to define or redefine the set of homomorphisms from this module to ZP. And then you wrote the right-hand side. And what is it? Is it the module of sequences convergent to zero?
Yes, it's zero sequences basically. Sequence.
So this is the set of sequences convergent to zero.
Yeah.
Again, we need such baby explanations for dummies. Otherwise, it's hard to understand.
Yeah, I see. Yeah. Well, in fact, I understand that my explanation of this. Of these constructions, they may look indeed quite abstract, and I mean to understand it better, it makes sense to look at the examples of ZP and also at the example of QP, which is not part of this framework. It's not a formal scheme, but still looking at what happens in these particular cases, it's very helpful.
No, but there is also another case. Suppose its ideal is 0 and R is a field. Yeah, you consider just
yes.
infinite dimensional spaces, products, and consider like continuous maps. Yeah.
Yes.
Yeah. Yes. It's already
No,
bizarre.
but then it's just a dual category to the category of free models.
Yeah, and then
category of the category of free models.
Yeah, and you then should bound cardinality to have small categories.
Well, yes, but yeah, as I said, I will ignore this.
Yeah, but then
you can think of this when I say models, you can think of this as int objects, and then you don't have.
But then to consider this as a compact object of something, it's really bizarre.
Yeah, it's I mean, it's unusual, but it's there's I mean it's still
okay. So it's really bizarre, but we have to believe Clausen and Scholze and the speaker.
Yes.
Wise people say that it's reasonable, and here I have to believe them.
Yeah, but I will repeat that in practice, you can bound the cardinality and then check that certain constructions they don't depend on this cardinality. Sometimes it's not straightforward, so it requires some work, but sometimes it's just immediate.
I think Maxim's concern was not about cardinalities, but about why the construction is reasonable. And of course, everybody should ask oneself why it is reasonable. But here we can just say that smart people have good reasons to consider this, and then we have to think more.
Yeah, but still the question. The question is very reasonable because sometimes it's not obvious that you can really bound this cardinality.
Yeah, but this is only test number 0 for this definition.
Yeah.
But yeah. Okay, anyway, we have to believe that this is reasonable to do.
Yeah. Well, anyway, I will comment more about this category, and in this particular case, it has alternative description, which is kind of more comprehensible. So we have the tensor product operation on this derived category, which is uniquely determined by the following. So on this product, we just defined it as the product over S cross T of the copies of the completion. I must say that such statements in this condensed formalism sometimes they're non-trivial theorems. But here I'm basically declaring that the tensor product is defined like this, just to define, to give a definition of symmetric monoidal structures. And we also require that the bifunctor commutes with colimits in each argument. The unit object is given, of course, by the one copy of the completion. And for M, we use this notation just like the value on the point, which comes from this condensed formalism, which is just our home from the one copy of completion to M, just the value on the identity object. We have internal home functor with respect to the tensor product, and more or less tautologically, to define some object, we need to define its values. I mean, to define what is our home from this product of copies of the completion to this object. And here, tautologically, we need to have that this is just our home from the solid tensor product to N. So this is quite standard. And non-trivial definition here is of the nuclear object. So an object is nuclear if for any small set. So when you take internal home from the product of copies of I hat to the identity object, then you take the tensor product, solid tensor product with M, and evaluate on a point. So this maps to R home from the product of copies to M, and this must be an isomorphism. The left-hand side, it can be considered as something like compact operators, but it's not so easy to make sense of this. Okay, I will comment on this later. But so for now, this is just formal definition.
Sasha,
yes.
We have to believe that this is a very good definition, but it's maybe precisely for this reason it's impossible to grasp it quickly. However, many years ago, Grothendieck, before he started working on algebraic geometry, defined the notion of nuclear topological, defined the notion of nuclear space, where space means topological vector space. Does this usage of nuclear refers somehow to Grothendieck's idea?
It does.
It does.
Actually, to elaborate on this, I would have to consider really the special case of ZP and QP. I didn't do it when I prepared the slides because the slides are they have to be of finite number of pages, basically. Yeah. But
because of cardinality restrictions, but it's just let me ask the following question. So there is this theory of condensed mathematics, which is not and is it true that the rationale for this theory is roughly as follows? So the naive idea would be to work with topological modules or topological vector spaces and consider the DG category or derived category formed by them. But this is not so good. And this condensed theory is a kind of better version of the notion of topological vector space.
Yes.
Is something like this good, true?
Yeah, that's true. And just to make it more precise, in this condensed formalism, when you have topological space or topological abelian group, I mean, all you want to remember from its topology is basically the collection of continuous maps from all profinite sets to this, for example, topological abelian group. Mm-hmm. And then you get sheaf, or you get a presheaf and you need to sheafify it on this huge side of all profinite sets, where the coverings are given by finite coverings.
Yeah, but this trick with profinite sets is well, it looks like a trick, but it's a trick to achieve a certain goal. And the goal, yes, I think, is, and I think you said that the goal is what I expected, that the goal was to define a better version of the, to improve the category of, let's say, complexes of topological groups. Complexes.
Yes, so I mean, with topological groups, the main problem is that it's not abelian, basically, because the image does not equal the co-image, yes, and So in this condensed formalism, when you, when you're considering shifts of abelian groups on some Grothendieck category, then this is abelian category. And so the point is that you want to consider things like R with discrete topology or R with usual topology, and the map from R to discrete, with discrete topology to R with usual topology. And you want to form all kinds of
you would like to form the cone of this map or the co-kernel of this map.
Yes. So the cone of this map will have 0 value on the point, but it will be still some non-trivial condensed abelian group. Yeah, and they have very reasonable technique actually to work with some with such objects, and there are a number of non-trivial results on this. For example, figuring out what happens with locally compact abelian groups. That, for example, you get the same X groups as in the usual exact category of locally compact abelian groups. It's non-trivial results, and this can be found, for example, in Scholze notes on condensed mathematics.
Sasha, maybe I have some question and remark.
Yeah.
So the first question is, in usual like functional analysis, when consider nuclear spaces, it's some abstract story, but there are some nice classes like nuclear Frechet space, like countable limit of countably generated Hilbert spaces and so on. Yeah, so something which what can really deal without large cardinals and so on. Is there some kind of like nice object in this story as well? So
well,
it's the end of the day.
It's also there are certain similarities. In particular, again, you can generate all nuclear object by some basic nuclear, and the basic nuclear are certain countable limits. There are some similarities.
Yeah, and also is second story is that I understand like this for kind of extension of topological groups, you get abelian category, and it's all tradition of Grothendieck to build derived categories from abelian categories.
Yes.
But these days it's not necessary. You don't have to start with abelian categories. You should deal in triangulated word.
Well, that's right, but still, it's you can, of course, you can consider derived category of exact category and still get a triangulated category, but still, in practice, it's not really easy to see what's going on. I mean, when you're looking at some concrete questions. You just get the abstract definition of derived category, and you don't know what to do, basically, how to work with this. Yeah, so I mean, it really seems to be a promising theory. But I wasn't going to explain it in detail. So I'm just mentioning the small part of it. Okay, are there any other questions? Okay, so let's denote by nuclear nuke of completion of R, the full subcategory of nuclear objects. And the following is a special case of the dualizability statement for sufficiently nice analytic rings, so that this category is dualizable. I mean, at least in this case of a fine Nasserian formal scheme. What I will explain next is how to describe the solid and nuclear modules in terms of the DG category of perfect complexes with torsion homology, which kind of simplifies the general picture, at least from my point of view, and also explains that everything makes sense for the abstract property GAlgebras with some modifications. So, as in the beginning of the talk,
can we have another break now?
Okay, for that, yeah, certainly we can. We should decide how long Sasha plans to continue. What is better? I mean, we can have a break and then you continue, or we.
Yeah, I mean it's fine for me. Yeah, I have quite almost infinite amount of time. So
of course you have an infinite amount of energy, but I'm already pretty old, and maybe I'm not alone in this company. So, the question is, during this break, can I ask you to think realistically about what, I think it's not so essential for us to predetermine how long we will listen, but Sasha, you can use this break to think about what can be really explained before we get completely tired. For instance, what you mentioned now looks appetizing, because I expect that perf I torus of R is something understandable. It doesn't require large cardinals and so on. So
yes,
it looks appetizing. So probably if there is a reformulation of all these notions in these terms, then explaining it's worth trying to explain it. But there could be other things which we simply cannot understand just because we are tired. So please use the break to think about what is realistic to achieve. Okay?
okay, yes.
Very good.
So how long is the break?
Well, probably 5 minutes, so maybe we can make it 10, but you know, it shouldn't be too long, because those who are tired, they will not get enough energy, and
so
other
people right?
fall asleep.
Okay.
Sash, maybe you kind of cut off the proof part of your talk and explain.
But I mean, I still I'd like to give some idea of the proof, maybe without all the explanations, but I mean to explain how this computation is done, because I mean it really resembles some kind of computations of projective tensor product in functional analysis, and it's kind of interesting that this makes sense in such abstract framework. So I don't know. Yeah. So if you already looked at the notes at the slides, then yeah, you see that the proof is quite scary, but I still I'd like to at least briefly explain what's going on.
Okay, so you like to scare us. Okay. I mean,
yeah, but on the slides there. Yeah.
Right, 5 minutes then.